All right. Welcome, everybody. Bill will be here a little bit later. He got caught in traffic. Apparently, one of the boom trucks hit a bridge, had his boom up, I think, and took the bridge out. So he's caught in traffic. He'll be here a little bit later. I'm sure everybody will just miss him so much. He'll probably get a kick out of that. But anyway, welcome to the High Voltage Live podcast. We got a couple of topics on here tonight we think you'll like. We're going to be talking about what is your accessibility, what's considered really accessible, and then we're also going to look at AC circuits, and we'll go through that in pretty detail. And then next week I'll cover the DC circuits, and I'll sort of show how to do the calculations and everything using a lot of the same values and how to go through that and determine those values correctly. And then we'll also got 5 new code changes, and we'll actually be up in Article 250 this week. And then we have our tool of the week, which is the red crimping tool. So Bill will be covering that. And we've already lined up our topics for the next week too. So I'd also like to give a little bit of shout out to NEC for Dummies. I was just looking at that before I came on, and apparently that thing's up to 17.4 now. And I got a feeling it's not going to be too much longer before that hits 20K. And I remember when we started, it was an existing group that had almost 1,000 members in it, I think. And we decided we were going to make that our main electrical code discussion group, and we started that really in earnest right about probably about March, 1st of March, somewhere in there. And it's already grown that much. So that's been pretty exciting watching the groups grow and all the good topics and everything that we have on there. But that's sort of where we're at with some of the groups. And I'm about to set up for anybody that's interested. I know we got a list of some of them that have already taken the spots, but we're also going to have the Monday morning coach where football season coming up, and we're going to have a lot of cool features and things I've been working on trying to get that ready. And basically what happens is everybody gets to pick a team, and you can be college, it can be pro, you can have one of each if you want. And we just come on Monday morning as a Monday morning coach, talk about what the coach did wrong and all that. And then, of course, we get to talk smack about our team if they did good. If your team did bad, you're going to get the smack from that also. So that's going to be a real fun thing. It's something I've always wanted to do. And I'd talked to Bill about it. And I said, I'd really like to do a football one because it'd be so much fun. And we're also looking at doing something totally different. We're going to have a fantasy league, maybe 2 of them. And you can pick other players from other teams, but you have to play the team that you pick. So in other words, your offense and defense will be your team. And then from there, when they're on a bye week, you'll have an alternate team you can play, but you're always playing your team because that's your team. So like I got the Cowboys, so I always will be playing the Cowboys offense and defense. So I'm going to have probably a terrible defense, but that's okay. It's all fun and everything. So we'll have a good time putting that together. But other than that, let's take a look here and look at our myth of the week. That's where we'll always go first. So I'll go ahead and key this up and get us ready for myth of the week.
It's time for Myth of the Week.
All right, let's take a look at the myth of the week. We got some really good stuff on here. Last week we covered the working clearances part of an arc flash boundary. What are the difference between the two? And this week we're going to look at what is really considered accessible. Now, when I started looking at this, I started sort of thinking we have a lot of different illustrations, but it doesn't really, we have a few that talk about accessibility and readily accessible and things like that. But there's so many different areas we could look at when we were addressing this. So what I decided to do here was put together a setup from the 2020 code. Now, they did make a definite change in Article 100 to accessible as applied to equipment. And when you get in and you start looking at these accessibility rules and things like that, there's certain things we want you to look at. And we also put in here that the main note to this was that no chairs, desk, or other items in front of equipment or equipment is not behind locked doors, elevated, or other affected means. Okay, that's where we get in and talk about it being accessible. And this is where it's applied to equipment itself. Okay, now when I look at this, I started thinking about this a little bit, and I was like, okay, now we have accessible as applied to equipment. You also have accessible as applied to wiring methods, and you also have readily accessible. Now, what I decided here was to go ahead and take a look at the definitions that are going to apply here. Now, as you look at this, what they're going to tell you is this. When you have accessibility as it relates to and applied to equipment, it just basically says capable of being reached for operation, renewal, or inspection. That's what is considered accessible. And then when you're looking at the wiring method portion, it says capable of being removed or exposed without damaging the building structure or finish, or not permanently closed in by the structure or finish of the building. So all they're really saying is you need to be able to get to it quickly. Okay, you have to be able to have accessibility without having to move something. Okay, now the next one that gets to be really interesting is talking about readily accessible. Now, a good example of this, let's say that you have GFCI protection and you take and have a receptacle that's underneath the sink. Okay, now I've seen this different ways, different inspections authorities, how they'll interpret this. And I've seen other instructors, how they view this also. And when you look at the definition, it specifically says capable of being reached quickly for operation, renewal, or inspections without requiring those to whom ready access is requisite to take actions here. Okay, now these actions could be using tools other than keys to climb over or under or to remove obstacles. Now, I want to talk about here to remove obstacles. To me, that's going to be the most important part, because I've heard some say, well, under that sink, they're going to put cleaning supplies and all other kinds of stuff underneath there. And you're going to have to take and remove those obstacles that are in the way to get to that GFCI protection. Okay, or to that receptacle. And I've sort of looked at this. I don't really see that being a problem, in my opinion. Where I see being a problem is if that GFCI receptacle is like located behind the disposal or something like that, the motor that's underneath there, then I consider that not to have ready access to it. And some look at it and they agree with that. Some don't. They say it's underneath. That's not considered readily accessible because I have to move stuff out of the way to get to it. That's an interpretation, however you want to look at it. Now, the informational note that's there, they talk about the use of keys is a common practice. And this is where you're under controlled or supervised conditions. And this is basically an alternative to the ready access requirements that are under supervised conditions that are in other articles of the National Electrical Code, or should I say other sections, really. And you have to just sort of take a look at this and have to make a decision on this. What are you going to consider to be readily accessible? Now, uh, uh, let's just say congratulations on becoming an official NEC Link affiliate. Oh, we are. I did not know this. I'll have to check into that. Um, I can tell you there's some other things that are going on um, uh, that I'm actually dealing with right now, and I'm waiting to see how all that goes. But some of the online training and stuff we provide, there's some things in the works right now that will be very interesting that could be happening here in the next few months. And as we get further down the line in discussions and all that, I will make it very available and let everybody know what's going on. But apparently, there's been a lot of interest in the online training. And a good example is like what we're talking about here. We'll have an illustration where we're in the kitchen and we may be showing where the spacing of your receptacles and everything is along the countertop areas and all that. And then we may have one underneath and we'll have the address for those um, ready accessibility issues. Now, the cool part about that is you can click anywhere on that illustration and see that information. So that
I made it.
be good. About time you showed up. They were all posting on here. Good, he's not here. I'm just playing with you, brother. But somebody had posted, "Congratulations on becoming an official NEC Link affiliate." I wasn't aware of that.
Oh, I don't know either. I don't know who that's from.
I don't either. Somebody put that on there, and I was like, "Oh, well, that's something interesting to know." But anyway, I was just explaining to them about the accessibility and everything here. Let me get this more in a full screen. And looking at the definitions, and I was sort of covering underneath the sink and explaining how some view it as having cleaning products underneath there, that would take and be considered as not being accessible, where some don't look at that as being that big of an issue. And I explained if I had the disposal motor there and it was located behind there, then I wouldn't consider that readily accessible.
Yep, I agree with that.
So I was just sort of breaking down a couple of things. That's where I'm at right now. Is there anything else you'd like to add to it?
Well, I had a job that I did, and it was two different districts. One was Boulder, the city of Boulder, and the other one was the city of Longmont. And I put both GFIs underneath the cabinet, and they were over towards the side, and they were up high, so you really couldn't, you could get to them real easy. And I did them both exactly the same. I had one inspector say it was fine. I had the other inspector say I want it moved. And it really wasn't a big deal to just, move it above the sink and then put the out, just change it around a little. Mm-hmm. I think it took me like 10 minutes to fix it. So it wasn't a big deal, but at the same time, it was kind of frustrating because it's like, I want consistency in the code. And, that's what I'm looking for. I want all the inspectors to be on the same page when it comes to stuff. I just, it's frustrating when one inspector says this and another inspector says no, and sure. So that's kind of where my whole thought is with trying to get kind of bust these myths a little bit and get it to where what does it actually say and where can I actually argue with the inspector and be right, or say, what, yeah, that probably is a bad place to put it for the customer, but in this case, these were both commercial spaces, and they were both both of them said they didn't care. I asked them ahead of time.
Sure. And that's what I was explaining to them. Some jurisdictions look at it different than other jurisdictions as far as what they consider readily accessible.
Yeah, and I wanted to say I really appreciated all the participation we had with from Nat King Code, and it was really awesome. I had so much good comments and so many good participation. The myth is that you don't need GFCI protection for a water fountain, and that's the myth, and that is false. The myth is busted. You do need to have GFCI protection for that water cooler. Now, I don't care how you do it. I don't care if you put a receptacle inside the water cooler and then put it on a GFCI breaker. Usually what I do is I just mount a GFCI right below the water cooler and then just run the cord out, plug it in. There was some talk that it's not required if you could put it on a regular outlet if it's integral, if the equipment itself comes with GFCI protection. I've never seen that. I have not seen that I've installed hundreds of them. I have never seen that manufacturer provide one.
Oh, wow.
And pretty much all of them that I've installed, we had to install our own cord even.
Oh, yeah.
So they just had the terminations in there, and we just had to run a cord out and then plug it into a GFCI.
Sure, and there's going to be a little bit more clarification in 210.8a dealing with the GFCI protection. We fully covered that in the new 2023 that's coming out. Matter of fact, we're in the process right now of editing it. I've already written all the changes, and I did a post on NEC, well, all the groups really, and we ended up in this cycle we'll be covering 237 changes.
Well, and that's going to be awesome because I can't wait to get my like 20 changes back that you get me from last cycle.
That had to do with the state, had nothing to do with the full one. But one of the cool things is I have a feeling most of them are going to cover about 150 changes, the other code changes, but I doubt they're going to cover as many changes as we're going to show. And I will say this for everybody that's watching the podcast, it's probably going to be important that you get a change book because there's a lot of renumbering of tables. There's stuff that's been moved around. They did a full, and I mean a full thing on Article 7, 24, 25, and 26. Now you're going to have Article 725 where Class 1 circuits were. That's now going to be Article 724, and Article 725 is going to deal with Class 2 and 3 circuits, and then Article 726 is going to deal with Class 4 circuits. And then they also took in Article 800 where you're dealing with Article 805 and 810 and 820, you're going to see a lot of requirements that were in those articles are going to be now general requirements that are going to be in Article 800. So everybody's going to have I'm just going to say is you need to have a code change book that's explaining where everything is and what took place. And I can tell you in ours, we cover all that, showing you what actually happened in this cycle of the code. So that's why we ended up with 237 changes. It's one of our bigger NEC changes book in probably 3 cycles.
Yeah, thanks for putting that up there. We got a code reference 422B4 for the drinking fountains and bottle fill stations. Thank you for that.
Yeah, I knew that was there. Okay, well, I think that takes care of the myth of the week. I don't see anything there. I appreciate all the comments coming in and everything. And I think we got that myth busted.
And the thing that's funny about this is I was going to like a bunch of schools. Like we had a whole bunch of different school jobs that we had to go do. And that's all we did was just go change out GFCIs in all the schools, just add GFIs. And it was kind of rough because a lot of them were roughed inside the water cooler, the bottle fill station location. So we had to junction box it and fish it down. And in the schools, they don't allow MC cable. So we'd have to use like steel flex and stuff.
Sure.
So it was pretty rough, but
awesome. Well, we're going to go ahead. I'm going to get started on topic of the week. Heck, we're already going 22 minutes already. But
I'm really sorry that I missed the Myth of the Week song. That's my favorite song. So, I was bummed out I missed it.
You can go back and listen to it.
I am.
I can send you a copy, brother.
No, it's
All right.
on you. It's on YouTube. So if you guys want, you can subscribe to Bolt Online Academy, ring the bell, and you'll get notifications every time we go live.
Yeah, I don't even promote that thing. It's just there for some videos here and there. And I think, heck, we're already over 50 people, and I don't even say anything about it.
Yep.
So, and I will say this: any of y'all that are doing this, y'all want to watch some good videos, go over to James Gray Stock up on YouTube. It'll be his training academy. He has, I don't even know how many, he's got a ton of videos on there. And he goes through doing full explanations on everything. And it's already, I mean, he just started it just a little while ago, and it's already up to like 700-800 people. He's getting so many views now that as soon as he gets to 1,000, YouTube has already contacted him, and they've already got uh, uh, electrical suppliers or equipment manufacturers that want to. He basically will get monetized for his channel now.
Nice.
So
Well, and
that
he
gives
he
you an
owes
idea
me
how good it is.
he owes me a hot topic for the conduit support.
Yeah, I'm going to get him to do that, and he was finishing some other things up, and we're about to get to ease a little bit, but we've been working round the clock. I mean, we literally been working 12 hours a day, and that's to get the code change book completed, and then we're going to do the updates for the code change book. So, for our other publications, and I can tell you, one of the things we do in our publications, there's a lot of references to codes, tables, even in our calculations step by step. We're going to have to change a lot of that. And anybody that will be testing on the 2023, you really going to need to know where everything got moved. And if you're taking the masters, for example, we have a full calculation in there. We show doing healthcare facilities. You're going to have to know that because there's new tables there showing the different calculations for the number of receptacles, whether depending on the type of location you are and what based on that location is going to determine the percentages you're going to apply for those receptacles. So if you're in critical care, whatever you're in, you're going to have to know that. And we're going to lay that out. So we're actually going to have to change our step-by-step procedure in the full calculation form so you know how to calculate that properly.
Yeah, I couldn't believe how much has changed. Like, I'm working in a hospital now, and I mean, with all the med gas and bed walls and all that stuff, I was just blown away, man. I mean, they are just stacking those. I mean, it's changed a lot since the last time I've done healthcare.
Yeah, there's a lot that you're going to have to look at, and but don't worry, we got it covered. We got even in our just the code change book's going to show you a lot of stuff. So I'd highly recommend everybody to anticipate the arrival of that. So,
And
all right.
I want to give a big shout out to NEC Live. They've been a big part of our growth with NEC for Dummies, and we've been sharing their feed every week, and it's really awesome to get all those top code people on there. I know James is probably itching to get back on there and do some stuff. So
Yeah, I'll
we're
probably go back on here. I don't know. I'll get in touch with Corey and them and Dean and talk to them, but it's going to be a little bit because I'm finishing a couple of things, and mainly I'm waiting for the code change book, and there's something else going on. I'm waiting to see what happens, and if that happens, I'll probably go back on and we'll have some things to talk about. I'll just say that.
Yeah. And one thing I was going to ask you, were we going to do that Monday morning coach? Or we going to do that Monday morning? Or are we going to do it Monday night? Because I don't know if I could do it Monday morning because I'll be working. I mean, I might be able to
Yeah,
do
we'll
it
just
like
call it
on
Monday
my,
morning, but we'll do it.
because I might be
We'll
able
do
to
it in
do
the
it like
evening. It won't
I
be in
might
the
be able
morning.
to do it. I might be able to do it like on my lunch break, but then it'd be like 1:00 your time.
Nah, we'll do it in the evening. We just
Okay.
call it Monday morning because it's the next day, So,
Well,
but we'll
it's
do it in
like
the afternoon. I
it's like they always say Monday morning quarterback, and you know what I mean. That was kind of our little
That's
joke.
right. Yeah, it's
All
just a
right,
joke.
cool.
At the first of the podcast, I brought it up and told everybody. And so I'm going to do a post here pretty quick, getting all that and anybody that wants to be involved. And I told them about us looking at the fantasy league doing that also. So
Yeah, well, it'd be a lot of fun. Get one guest on every time, and then
yeah, it'll be
we can
awesome.
battle. Yeah,
Talk smack back and forth. Love it.
yeah, yeah. I don't
Okay,
know.
let me get it.
Curse is coming up, and William Curse, if you're watching, I don't know about your Jags, man. I watched them against the Raiders, and it was like they fumble, then the Raiders throw a pick, and then they fumble again. It was
That's
pretty
right.
bad, but I know that wasn't their starters either, though.
Yeah, it's going to be fun. I'm looking forward to doing it because I love football. So I love
Yeah.
college and pro, so I don't care. All
All
right,
right,
let's
we'll roll
choose
the topic.
topic of the week. Ah, ah. Okay, now looking at the topic of the week this week, what we're going to be looking at is AC circuits. Now, uh, everything that you will be looking at here is where we're going to get into uh, these circuits, and this all comes out of different books that we have. You could actually go into the Journeyman, which is where I took this from, or you could even be looking in our generator, motor, transformer, compressor. We discuss different things in there as it applies to those different items, and then we also do it also in the design book.
So
Now,
now up top, we're looking at an AC sine wave.
yeah, yeah,
Okay.
and what you look at first of all is when you have an alternating current. Basically, how is that defined? It's basically current that periodically that will change direction and continuously changes a course and magnitude. Okay.
Mm-hmm.
Now, when you have these currents, they start at zero and they build up to a maximum in one direction, and then it falls back to zero and builds up to a maximum in the opposite direction. And then, of course, it returns back to where? Zero. Okay.
Yep.
Now, when you look at the values of alternating current and voltage, this can be indicated by using, of course, what you're looking up there. It tells you the maximum, it says the AC sine curve. That's in the illustration.
Yeah. So is that called single phase or two phase?
That'd be single phase there.
Okay.
Now, when you look at this, what does the curve represent there? It's going to represent a definitive voltage or current value for a certain degree of rotation through the alternating cycle. And then it'll tell you as you're looking at that, one cycle begins where? At 0 degrees. And then from there, it ends at what? 360 degrees. And that
Right.
value of alternating current is zero at 0 degrees, and then the maximum in one direction at 90 degrees, and then zero at 180 degrees, and maximum in the the opposite direction at 270 degrees, and then it goes back down at 360 degrees at what? Zero.
Right.
Okay. Now, when I start looking at this as an example, I'll give you an example of this as I
So
was
what
thinking
that
about.
illustration is showing, they're 180 degrees opposed, correct?
Yes, you go 0, 180, then another 180 gets you
10-4.
360.
Gotcha.
Right.
I wanted to get
Now,
this real quick, James. I did miss you guys this week on NEC Live. I was real busy at work. I totally missed the whole show, but it was really a great time with Ryan on there, and there was a lot of things I learned. So I still watched it and I still shared it to NEC for Dummies. So
Sure.
really good show.
Now, as an example, let's say that you had a single loop of wire that can be placed so that it rotates in a magnetic field. Okay. As the loop turns, the sides of the loop cut through those lines of force. And after you do that, what ends up happening, you have an electrical magnetic force that is induced in the sides of the loop. That gives you an example of why you have the alternating current there. Now, as I look at this next illustration, I'm going to point out there's a lot of things here and talking about how induced voltage produces current flow. And as an example in the illustration, if you look at the side there, AB, it's moving up through the field, and the side CD is moving down through the field. Therefore, as you look at this, the voltage induced in AB causes current flow from A to B, and the voltage induced to CD causes current flow from C to D. Therefore, you're adding this up. Such voltages add together and cause current to flow in the direction of what? A, B, C, and D.
So is that like a right-hand rule or is that a left-hand rule in this diagram?
Right hand.
Okay.
Now, as you look at this action that's taking place here for as long as, I guess say, is AB is moving up and CD is doing what? Moving down.
Yep.
Okay. Now, when the coil is in the vertical position, the sides are going to be moving horizontally and parallel to the lines of force, and no voltage is induced. However, looking at that, as the loop moves through this position, the sides A and B rotates down through the field, and the side CD does what? Rotates up.
Yep.
And that gives you an idea of the principles when you're dealing with alternating current. Okay. Now, also, I'll point out when the current is connected to an external circuit by, say, the action of slip rings, the current will travel in one direction while the loop rotates from 0 to 180, like we were talking about a while ago.
Right.
And in this direction, while the loop rotates from 180 degrees to what? 360 degrees.
Mm-hmm.
Okay. Now, while it's in the vertical position, the loop, as you're looking at the illustration, is either in the 0 to 180 degree position and no voltage is induced. When the loop is rotating in the horizontal position, the maximum voltage is induced due to the sides cutting the greatest number of what? Lines of force. And that's what we're talking about there. You can see those lines of force that we have in the illustration between the north and south. Okay. Now, the due to these, let's say I want to say this, the alternating current sine wave is utilized in this case to represent the values of voltage or current from where? 0 to 360 degrees. And that's how that alternating current circuit works, showing the sides A, B, and also from C to D.
Right.
Okay? And that gives you a basis right there of the principles of what an alternating current is. Okay.
Right.
Now, the next thing I'm going to look at here is I'm going to get in, and we took and put some illustrations here that are going to talk about effective values. Okay. Now, there's a lot to look at here. Now, when you determine the amount of power that's available from an alternating current power source, you have to determine what the effective values are. All right.
Right.
Now, obviously, when I'm looking at this, effective value does not equal maximum value because that value is reached only once in the cycle. Okay. So I want to
So
point out,
is that referred to as your true RMS, or is that slightly lower than your peak?
it's not your true RMS.
Okay.
And it'll be slightly lower. It's not going to be, because when you look, well, let me get through this and I'll show you.
Okay.
you'll see we put in there, we talk about the effective RMS value of a pure sine wave, and
Right.
and that's I guess it would be peak value, but what I'm trying to say is we're looking at doing this from a pure sine wave and determining an effective value. Okay.
Gotcha.
And
Okay.
and if you look down there, you'll as you're looking at the illustration, you'll see we talk about an effective value during negative half cycle. And
Okay.
then you got a peak value where you have an effective value. Okay. So what we're doing here is basically determine what the effective value is to be applied to this alternating current circuit.
Okay.
Now,
Gotcha. So
now,
this would this be like a sine wave that is like, is this like a theoretical sine wave that's not under
yeah,
load then?
yeah, it's theoretical.
Okay.
We're just putting some values here to explain all of this. Okay.
Gotcha. Okay. Okay.
Now, when I look at this, we'll tell you obviously that effective value does not equal maximum value. And that's why I was trying to explain there as you're
Right.
looking at that illustration. Now, because this value is only reached once in what? In the cycle.
Yep.
Okay. Now, during one half cycle, the current is equal and opposite in direction, so that during the other half cycle, the currents don't do what? Cancel out each other.
Yep.
Okay, that's why you have effective values in there. Now,
Okay.
I will note something here that work is being performed whether the current is moving in one direction or the other. And if that's the case, the effective value lies between the zero value and the maximum value.
Right.
Okay.
Well,
That's
I know that it drops like when you put it under load. Like if
mhm,
you were looking at an oscilloscope, you'd see that sine wave be high, and then the minute you put it under load, it's gonna drop. That sine wave's gonna like tighten up and lengthen.
sure. And when you look at that effective value of that alternating current, when we look at it and we're calculating, it's by comparing it with what? Direct current, actually.
Yep.
Okay. So when I look at this comparison, it's going to be based on the amount of heat produced by current under the same conditions of use. And that heat that's produced by that current is always proportional to what? The square of the current.
Right.
Okay. And since that's the case, it is necessary to determine the square root of the mean square of the number of instantaneous values. So when I look at that, I look at the RMS, which you were asking about the root mean square. It's
Yeah.
a resultant current value, and it is calculated using a formula, which is I equals IM divided by the square root of 2.
Okay.
Okay. That's how that's going to be determined.
Gotcha.
Now, as I look in the formula, what is I? Okay, I in the
Amps.
formula is the effective value, and IM is the maximum. So
Okay.
we tell you, and that's why I gave that formula. If the maximum current has a value 1, then the RMS is equal to 0.707.
Right.
And that's determined by I equals 1 divided by Z, which is the impedance, times 1.414. And that will get you 0.707. Okay.
Okay.
Now, when I look at determining the effective value of an alternating electromagnetic force, this can be determined by multiplying 0.707 by the maximum EMF. Okay.
Right.
So when I look at all that and I look at the calculation and applying it here, let's just pull out the values. Well, I'm going to show you here. We already determined by me explaining that calculation there where the 0.707 comes from.
Right.
So I'm going to look at doing my effective value here, amperage, and I'm going to take the Imax and I'm going to take that time 0.707. And if you look in the illustration, what is that Imax at? It's at 10 amps at peak value. Well, if I take 10 amps times 0.707, that's going to give you an effective current value of 7.07 amps.
I am gonna call foul on this one.
How come?
That is too easy. No, I'm just kidding. That's way too easy.
Well,
That's awesome.
everything that I'm explaining here, it's explained just like that in the publications. And
Right.
what we try to do is get this set in such a way where people can follow and understand what the average values are compared to where you're at peak value and you're at a negative at a half cycle. So you
Right.
understand what that sine wave is and how it is applying as it relates to dealing with an alternating current circuit.
Right.
Okay. Now, the next thing,
And we got a first timer in here. First time High Voltage Live podcast.
awesome.
Awesome.
Thanks for coming in, brother.
Yeah.
Now, I'm going to show here, this is where we got the sine wave, and we're going to show this for the instantaneous amps here. Now, you're going to notice we're going to show you 10 degrees sine is 0.1736. Okay. Now, if I look at doing my effective amps here, you'll see we'll show you right over on the left hand side of the illustration. We do it at a different way this time. We're showing you 60 amps. Okay, at the peak and at the negative end. So you'll see 60 amps. So you take 60 amps 0.707, that gives you 42.42 amps of effective current. But now I also want to look and determine what the instantaneous current is. And all you're going to do here at 10 degrees sine wave, that's going to be 0.1736. And I'm going to get instantaneous amps here of 10.41 amps.
Okay.
So all you're really looking at here when you're looking at this alternating current, you got your current in amps. You're always going to use that. But if I'm doing the effective, I'm going to use the value of 0.707. And if I have 10 degrees of sine wave error, I'm going to use 0.1736 to help me determine what that amperage is for the effective and instantaneous.
Right.
Right? And that's about as easy as it can be explained for you.
Absolutely.
Now, let's take a look here. This is going to deal with frequency. Now, I want to explain something here. I've already explained that one cycle of alternating current covers, let's say, a time in which the current value increases from 0 to the maximum in one direction. Then, of course, it returns to where? 0.
Yep.
And then it increases to a maximum in the opposite direction. Then once again, it returns back to where?
0.
0. Okay.
Yep.
Now, the number of cycles per second is what we referred to as the frequency of the current. And these cycles are commonly called what? Hertz. Okay.
Yeah. A question for you. So, typically you'll see like European equipment be at like 50 hertz, and
Mm-hmm.
you'll see like US equipment at 60 hertz. Is
Correct.
there any kind of a reason why you couldn't use those different hertz systems together? Like, is there an issue with using a 60 hertz equipment in a 50 hertz system, or using 50 hertz equipment on a 60 hertz system?
I would say there'd be a problem there because the equipment and stuff is designed based on the rating of the hertz,
Okay.
and I would have to do a little more checking on it because I've never actually been asked that before.
Okay.
I'm not 100% sure.
I thought it could have something to do with the listing of the equipment.
Yeah, I'm thinking there's something there. Because I don't deal a lot with anything from overseas per se,
Okay.
and I'm not really sure if the 50 hertz equipment. Well, I got an idea. It won't. Okay. Well, I just did some checking because we did a case on that. Dad was dealing with a case that dealt with that, and he said it doesn't affect it at all.
Nice. Okay.
So
Hey, that's pretty weird how you just reached out to your library.
yeah. Well, I wasn't on that particular case when he was doing it, and I knew there was something. That's why I said I wasn't 100%.
Ooh, we got
sure.
a comment came in. Motors will run slower if rated for higher frequency and operating on lower
That
frequency.
that's true. That's what I was thinking of, if that would cause a problem or not. But
Well,
apparently,
it makes sense because it does it in a freak drive.
I know. But we did a thing on that, and apparently it's okay. I was thinking about something running slower because of that, and I was like, I'm gonna have to do a little more checking on that.
Well, you
But
think about it, you do it with nominal voltage. You know, you run some stuff at higher voltage, you run some stuff at 240, run some stuff at 208. Doesn't make it like a violation or anything.
that's correct, and that's what I wasn't sure of. I was more in my mind. I was thinking about something running slower if it affected or not, and I'd need to do some checking. But apparently, we
All right.
did a case on that. And Dad, I'm at the office. He was listening. He goes, "No, no, we're good." So I said,
All
"Okay,
right.
all right."
Well,
So
because I know sometimes the HVAC equipment comes out as 50 hertz, and then they're like, "Are we supposed to do a different calculation or something?" But that's cool to have pops in the background. Tell
yeah,
them thanks, appreciate it.
I will. All right. So then when I look at this and you're looking at the frequency of the alternating current, it'll affect the operation of electrical circuit and equipment. We're operating on a current with a certain frequency, like we were just talking about. And that's what I was sort of thinking of. But it will affect it, but it'll still work on the system, I guess, is what we're trying to say. So also, whenever you're looking at wherever such equipment is used, um, I would say at that case, it must be designed for the frequency of the current in the circuit in which it is be supplied. And if it's not, that's going to cause it to run slower. Okay.
Okay.
Now, looking at the illustration itself here, um, you'll see that we have values that are set up here. And we'll tell you when you're setting up the formula, you're going to see A equals Q over your frequency, and Q is going to be the column. Okay, and you'll see at full charge, we're going to show you one column, and then we're going to show you our frequency is at 60 hertz. So all I would take is that one column, and then when you're looking at doing the hertz, you'll take one, divide the 60 seconds into it, and that's going to give you 0.0166 seconds. Divide that into it, and that's going to give you a current in amps due to that electron flow frequency and time of 60.24 amps.
Okay.
And that's how we look at the frequency when we're dealing with alternating current circuit. Now, the next thing you're going to look at is dealing with the phase. Now, the phase of the alternating current or voltage, this is going to be in an angular distance, and it's where it is moved from 0 degrees in a positive direction. And that phase angle is the difference of rotation between two alternating currents and voltage, or between a voltage and a current. As an example of this is when one voltage reaches a maximum value, say of 30 degrees later than another, there's going to be a phase angle of 30 degrees between the voltages. Okay. Now, if you look at an alternating current circuit, what does that mean? It means the current lags or leads the voltage, depending on where it is in relation to the alternating current. And as you're looking at that, this is due to what? This is due to the inductance or capacitance in the circuit. Okay. So in other words, in circuits where the currents or voltage do not reach maximum at the same time, such currents and voltages are going to be at that point considered what? Out of phase.
Right.
Okay, you see what I'm saying?
Yep.
Now, when you look at that, if I'm looking at that illustration, just to give you an example, we're telling you there, if you look at the bolded line, the more bolded black lines, that's where the line is crossing the 0 degree line before the lighter line has crossed it. And this, if that's the case, what does this indicate? This indicates that the current reaches 0 degrees before the voltage in the peak value of the voltage occurs. So since that's the case, therefore, what happens, the current is leading the voltage in the illustration.
Okay.
Okay.
So is that always true, or is that just true in certain cases?
Well, like I was saying before, when you look at the as I was giving an example, I was saying that when you look where it talks about, you get in where you have a phase angle there, and it depends where it is in the circuit, whether it leads or it lags it.
Okay, so sometimes it could be
Yeah,
opposite.
yeah, and that's what I
Okay.
was saying. When you look at that, I was saying uh, in an alternating current system, I was just doing like a little note. I said the current lags or leads the voltage.
Okay.
And why is that? The reason that's due to inductance or capacitance in the circuit.
Oh, gotcha. Okay.
Okay.
That makes sense. Okay.
Yeah. It depends on what you're doing, where it's at in the circuit and what's there. Okay.
All
Now,
right.
the next one here, we're going to look at, I'm going to go past that because I've already explained that,
Right.
is looking at capacitance. All right. Now, what is capacitance? Capacitance is going to be the property of a circuit element, and this is to permit it to store basically what? A charge of electricity.
Yep.
That's basically what capacitance is. That's why you got capacitors and everything there. Now, when you look at a capacitor, um, it's also at times it's known as what? A condenser. Okay. It temporarily stores an electrical charge and consists of two metal plates separated and insulated from each other by using what? Dielectric material. And when you look at dielectrical material, what is that? That's a non-conductor with a specific amount of resistance against current flow. Okay.
Right.
Now, when one plate of that capacitor has an accumulation of electrons, the electrons on the other plate will do what? They'll push away.
Right.
Okay. And when that happens, that means one plate will be negatively charged and the other plate will be what? Positively charged.
Hey,
Okay.
just a quick question for you, James. I know they do like all these statistics on like people dying from electrocution, and that's why it drives a lot of the GFCI requirements, and that's kind of what I was thinking too with this water bottle fill station, water coolers. Like probably good that it has Class A protection. Is there any kind of statistics that you know of off the top of your head for like people dying off capacitors? Like, I mean, because that's they could be storing some large
Yeah.
amounts of energy.
If you go to the 70 document, the
Uh-huh.
70 document, we tell you when you're going to work on it that you have to release the power off of those capacitors before you work on it. You have
Oh,
to do.
so that's to ensure electrically safe work conditions.
That's correct.
Okay.
And it's in there. And we basically, it's funny when I was teaching for our, when we go out for an FBA and I do a 70 course, we actually go through and explain that this is another means of source that could get you, and therefore you have to drain that off the ground.
Okay. Okay.
All right.
Discharge. They basically discharge the
Sure.
energy, stored
Sure.
energy.
Matter of fact, in our 70E publication, we even talk about that. And we have notes and stuff in there telling you certain things that you need to do in
Well,
order.
I knew something because Willie Jackerson was saying that he likes to be the energy discharger of those things, and he likes to pull arcs off of them. So I don't know. It's weird. I don't know why he likes doing that, but I just
Well,
wondered. I was
and,
just curious.
and that's a good question. That's one of the things that you'll run into. And that's why we take in our 70 publication and lay that out to explain how you go about determining. So, in other words, if I had I was doing an energized electrical work permit, that would have to be another note that's put in there before you work on it, that
Okay.
you have to de-energize that and bleed it to ground. Got to discharge it. Okay. So
All right.
then, so if I'm looking at an alternated current charge, and it's be applied to that capacitor, condenser, whatever you want to call it. The negative charge on one plate will cause a proportional positive charge on the opposite plate, as the charge on that first plate that's there, it'll be considered there to be positive through the sine wave, and the opposite plate will change proportionally to what? The negative charge.
Okay.
Okay. And then when I look at this and I start looking at getting ready for the calculation, you're going to have a unit of measurement, such as what we'll refer to here as the farad. Okay.
Okay.
And with small capacitors, often they're measured in microfarads, or it'll be a farad and it'll be point, and I think it goes like 6 zeros and a 1. Okay. So we'll look at that in the calculation. And when I look at the symbol for that microfarad, it'll be MFED. And therefore, we'll look at a capacitor with a maximum amount of electrons. That is going to be considered to be what? Charged.
Yep.
Okay. Now, also, I want to point out.
So are you saying that as a capacitor, when you charge it, it has like a maximum? There's no available above that, so that's how the actual capacitor is rated.
Yeah, you'll notice in the illustration, we're going to show you two different ones, the rating based on whatever the rating of that capacitor is. And you'll see us do it in a series circuit, and we'll also do it in a parallel circuit.
Okay. So that's if you want to achieve a higher voltage level, you just parallel them?
Yes.
Or no, you series them. Sorry, I said parallel. You wouldn't parallel them, you series them, right? Because that illustration in the middle is series, right?
Well, the one in the middle is a series. And when you do the calculation for that, that's going to get you a total capacity of 4. And when I do it in series, you're going to, parallel, you're going to get 36.
Okay, yeah, I'm sorry. I was trying
you were wrong on that one.
Yeah, I was trying to understand your illustrations. That the top one's parallel, right?
Yeah.
And then the middle one is series.
Correct.
Okay, 10-4. Gotcha.
Okay.
I don't mind being wrong. I'm wrong a lot.
Yeah, I was trying to think where you were going with that.
Well, I just wanted to see, like, on the illustrations. I was trying to follow the illustrations and just see how to achieve that higher power level.
Yeah, but I could take and just go through this and show the calculations, but anybody that's watching this video, I want them to have an understanding how all this applies, and what it means.
Gotcha.
So if I'm looking at it, and let's just say you're talking about the surface area of plates, that's going to be the distance between the plates and the dielectric material between the plates, and all the factors that are going to affect the capacitance of that circuit also.
Right.
Okay.
Well, now, we got Jake Riddle here for the first time coming in from the 2023 Code Ninja side of Facebook. So that's pretty awesome. Appreciate you being here, Jake Riddle. And he's an awesome guy. So I've been talking with him a lot. Really intelligent individual.
All right. Now, when I look at this and I'm looking at a capacitor, it's connected in series with the alternating current circuit. That current is allowed to flow back and forth in the circuit without actually passing through what? The capacitor.
Right.
Okay. Now, I also will point out here that the electrons are going to build up on one plate of the capacitor and flow out through the other plate. And an electrostatic field is established that causes the current to flow in the opposite direction. However, as those voltages from the source begins to drop, the electrons start to flow away from one plate of the capacitor onto where? The other plate.
Right.
Okay. Now, since that's the case, the basic effect of a capacitor in an AC circuit is to cause the current to do what? Lead the voltage.
Okay.
All right.
Okay.
And that's why I was explaining that.
Yeah, because it's pushing the electrons out in front.
Hold on a second. What?
Here's that form of that 50 hertz. They used in circuit 50 hertz, and here where the 60 is, you can see it makes a difference in operation.
Oh, okay. Cool. Which book's that in?
That's in our Generator
Oh, okay.
control.
Well, I didn't even know that was in there. Okay. Well, Dad just
Tell him to
showed me
figure
something.
14
He was showing here in the generator transform motor compressor book, and you look in we have an illustration 14-13 and talking about the slip, right? And we're showing where you had a 50 hertz here, and it does affect the operation of that motor, lowers it down, like somebody questioned on there a while ago. So yeah, we actually have this showing you how to do that calculation at 50 hertz and the difference when it's at 60 hertz, and it does affect the RPM. We actually show you here the RPM is at 1800 RPM based on, I'm not going to go through the whole problem. And then when you do it at 50 hertz, it was at 1710.
Okay.
So
Well,
we
and
actually have that in there.
yeah, and it makes sense why the inspector had that concern, because there was some HVAC equipment, and he was like, "Are you sure you did all that calculation?" And I didn't even know, because somebody else supplies the HVAC equipment, and we just hook it up, and they're like, "Oh, you're gonna have problems here," and I didn't know. I was just, to me personally, I was like, "Okay, these guys give me prints, and they say here, hook it up at X amps." Now, when it shows up 50 hertz, I'm still
Right.
hooking it up at the same amps, and then if they got to change out the unit because it's a European. To me personally, what I thought in my head was that it would be a listing problem, that was not listed for a 60 hertz system.
Yeah. And that's what I was saying when I said it first. I said, I think that would be a little bit of problem. And that's why I was doing it based on the comment that come in, but I'd had to do some checking on it. But I could see where it could be put on the system, but it's going to, the RPM on it's going to be different. And that's what I was getting to when I was talking about that.
Yeah, and like Willie Jackerson always says, "Oh, do you just put more freaking bigger wire on it and it'll go faster?" I'm like, dude, I don't think that works like that. But
Sure.
he's out of control.
All right. And like I was saying, when I look at the basic effect of that capacitor, it was for the current to lead the voltage. So if a circuit could be designed for, say, just thinking about this, without any resistance, the current would lead the voltage by what? 90 degrees C. And that's where we got in talking about inductance, capacitance, and everything a while ago. And I was explaining that. So this, as you look at this, and you start looking at the calculation based on all that information, and I look at a series circuit, you're going to take, we got 3 capacitors in series at 12 microfarads. Well, you got 3 of them, so all you're going to do is take that 3, divide it into 12, and that's going to give you 4. Okay. Now, if I do it in a parallel, all you're going to do is take all 3 of those rated at 12, and that's going to give you 36. So the easiest way to remember this, if it's in series, you take the number, divide it by whatever your total microfarad is, and then if it's in parallel, you just add them all up together.
So what would be the advantage of doing a series one? Is that for like more of a controlled capacitance?
Yeah, it'd be a controlled capacitance.
Okay.
Now, let's look here. This is where you look at the reactance of the circuit. Now, I'd already made comments about capacitive reactance and talked about inductance earlier. Now, what is the effect of capacitance that when we're dealing with an alternating current circuit? Basically, I look at it this way. It's similar to that of resistance to current flow. And when I look at that, that's why we would refer to this as capacitive reactance. Okay. Now, when you look at that, if that is the thought process, then naturally what that means is the capacitive reactance opposes what? The current flow in a circuit.
Right.
And therefore, if it's opposing it, it's sort of like Ohm's law. When I did Ohm's law and I was showing doing the calculation, it's something that opposes it. Therefore, since it's opposing it, and we look at anything that deals with capacitive reactance, inductance, things like that, we're going to measure that in what? Ohms.
Right.
Okay. Now, based on that, capacitive reactance in a circuit, that means it's inversely proportional to the capacitance and the alternating current frequency.
Right.
Therefore, if the frequency increases, the capacitor charges and discharges more times per second. Therefore, that means more current does what? Flow in the circuit.
Yep.
Okay. Now, based on that, just to sort of combine that, what does that really mean? It means reactance decreases as capacitance or frequency increases.
Right.
Okay. So looking at the illustration, we show you the formula up here, and XC is going to be your capacitive reactance, which of course is in ohms. F is your frequency, and C is going to be your capacitance in farads. Okay.
Right.
So you're going to take XC when I'm determining the capacitive reactance. That's going to be 1 divided by all those values. So
Right.
I'm going to look at this.
Which is basically a reciprocal.
Sure. And you take these formulas. The only thing we're showing you in here that you need to add here, we're telling you got the capacitive reactance in a circuit, and we're telling you got a frequency of 60 cycles or hertz per second and a capacitance of 200 microfarads. So I'm going to take that 2 times 60 hertz times the 200 microfarads, divide that by 1 million, and that is going to give you a value in ohm rating of 13.26 ohms for that circuit.
Right.
When I'm learning what the capacitive reactance is. All right. Now, we just talked about, also, I brought this up earlier, dealing with inductive. Okay. Now, what is, first, let's look at it this way. What, instead of saying inductive reactance, what is inductance? Okay.
It's kind of inductance. Is that similar to resistance?
Well, when I look at it, it's exactly opposite to that of the capacitance. Okay.
Okay.
So when I look at inductance in an alternating current circuit, what this means is that the current is going to lag the voltage, where capacitance does what?
Leads the voltage.
Lead the voltage. Okay. That's the alternating effect on this. All right.
Yeah, and like the only reason I would say inductance is because like if you get inductive currents, then that would actually be kind of like bad to your circuit, and it would act like resistance.
Sure.
If you had too much inductance.
Here's a good explanation.
Oh, we got a big comment came in. This is Jake Riddle, I believe.
Yeah,
Okay.
sure it does.
Yeah.
Sure it does. I don't disagree with that at all.
Yeah,
he's
no.
correct on that.
Yeah, good comment. Thanks,
Yeah.
Jake.
Yeah, I'm not going to be getting into all those different things. I'm just going over the basic principles.
Yeah,
now.
and it's awesome that a lot of the apprentices come up to me and they ask me stuff, and I'm like, I don't know, I got to ask. I'll ask next time.
Sure. Well, it's just like you were asking. Whenever you have a current change in an inductance coil takes place, which is what you were explaining, basically what happens here, an electromagnetic field is what? It's induced at that point. And that means this is which opposes the change in what? Current. And
Right.
that's basically what inductance is doing. So the electromagnetic field induced will be the maximum when the rate of current change is what? At its greatest.
Yeah.
Okay. So the current change at that point is most rapid in this AC circuit when it is passing through where? The 0 degree point.
Yep.
Okay. And this action, when you're dealing with it, that causes the induced voltage to be at what? Its maximum at that point. That's basically what we're talking about.
Well, and that's what's funny. That's I really enjoy the IAEI Live with Thomas Dimitrovich, and he's an electrical engineer, and he does a lot of stuff on this. And one of the cool things that I learned, and I love this, is he's like, the 0-point crossing is almost impossible to predict.
That's right.
And I just love that, because it's like, that's what these engineers are trying to do with like these interruption ratings, is they're trying to predict. And what they're trying to do is predict where it is before that 0 point. Like, they don't want you to have like an arc event of 65 AIC. They want to anticipate that ahead of that, and they don't want to wait till that 65K goes to 0 point crossing.
Sure.
They want to anticipate that, catch it way before that.
And that's why I was talking about the 30-degree phase angle.
Yep.
Trying to explain that. So
absolutely,
when you're looking at that, basically what that means is what is the effect of inductance on an AC circuit? Well, that's going to be called that inducted in currents, because it impedes the flow of what? Current in the circuit.
Yep.
Okay. Now, when I look at the inductive reactance here in the AC circuit, what is it? It's proportional to what? The inductance and the frequency.
Yeah.
Okay. And as inductance is increased, that induced electromagnetic force that opposes the applied EMF is increased. Therefore, the flow of current becomes what? It reduces. And that's what you're talking about. Depending on if you're capacitive or your inductance, that's what those engineers are looking at. And that's why you got that 30-degree angle there.
Yep.
Okay.
Yep. And that actually comes into overcurrent ratings, where they're trying to interrupt it at half a cycle, or, when you're using the up, over, and down method, then, you can actually code compliantly interrupt it at like a full cycle, but all your selected coordination has to match.
That's right.
It has to be a tested pair. If you don't have that all matched, then you can't use the up, over, and down method.
Sure. And when you look at that, based on that, so when the frequency to that current is increased, then naturally that means the rate of current change in the inductance coil is also what? Increased.
Yep.
Okay. And when you have that induced electromagnetic force, which opposes the applied EMF, therefore it's higher, and the flow of current is once again done what? It reduces, doesn't it?
Yep.
Okay. So,
absolutely.
So when I look at that and I apply this calculation here, the unit of measurement for the inductance, once again, just like we did for the capacitor reactance, is going to be rated in what? Henries. Okay.
Yep.
Now, if I look at this, and that's why we were discussing this earlier here, you're going to do the same thing. Got the inductive reactance XL equals 2 times pi times F, which is your frequency. Of course, that's the current. And then you got L, which is your Henries. So I'll take the values we give you there. We got 10 Henries connected in a 60 hertz circuit. So I'll take 2 times pi, 3.146 times 60 times 10, and that will give you an ohm rating of 3,769.92 ohms.
Wow. And dude, that is so cool how you break it down like that. And one thing I want to give a shout out to Henry. Remember working with me, bro? I got you one. I got you a solid, man. I got you a rating. Everything's rated in Henrys now because of you, bro.
Now, the cool thing about this is you can see now how the breakdown is happening to go through this whole AC circuit. And I'll say this for the people that are new, got apprentices and stuff, I've always said it's important to have it explained so you actually understand what is an alternating current circuit, what are the effects behind it. And as you look, we did capacitive reactance, inductive reactance. Now you're looking at impedance. What do all three of those have in common?
They're
all rated ohms.
They're part of the Ohm's law.
That's right. And people always say, well, how did you determine getting this when, like when we were doing Ohm's law and pi formulas and I was giving you values. Values are based on this, and this is how it operates through an AC circuit. So when I look at impedance, what is it? This is where you have the current, and it's in a purely resistive circuit is equal to the voltage, which of course is divided by what? the resistance.
Right.
Just like I was saying, just like we did everything else. So when I'm looking at the AC circuit, capacitive reactance and inductive reactance must be considered before the total in a circuit can be found. And that's why I was showing how you do that. Even though we give you known values when we're doing illustrations, this is how you get to those known values, knowing what's in the circuit in order to determine what that impedance is for those added together, so you can divide that into the voltage to determine what the amperage is.
Yeah, and like I say, there is no question that's stupid at NEC for Dummies. If there's people in there that in our group in NEC for Dummies that call your question stupid, let us know, because the worst question that you can ask is the one you don't ask. And so we're really open to all perspectives. We're really open to anybody that wants to post a question. Don't be scared. I mean, you can post anything you want, any question. I mean, I asked probably the stupidest questions out of anybody to James, and I'm not scared to ask a stupid question, because I'd rather ask a stupid question than make a dumb mistake. So that was just my little shout out for the NEC for Dummies. If your apprentice is in there, we got a lot of top code people in there, and a lot of the top code people are a little bit arrogant, and you have to kind of take it with a grain of salt. I really love the quote that I heard from Ryan that he saw, that he said, a small amount of humility will save you from humiliation. And that's a really good quote. And I try to be that way. I try to be humble and just say, you know what? I'm learning from James. I'm learning from the Stall Cups. I'm learning from these top code dudes. And I don't know it all. I don't know all the theory, and I'm trying to learn the same time everyone else is. So,
and when you look at this, just sort of tying this together, you take the resistance, capacitive reactance, inductive reactance, and when you add those together, basically, what is that called? The impedance. Okay, so the way I like to look at this, when I'm explaining this, in determining the capacitive reactance, inductive reactance, and resistance, you cannot just take those values and add them together. And the main reason behind this is because of what? Due to your capacitive reactance and inductive reactance and alternating current circuits have an opposite effect. So in other words, what does that mean? Just like we talked about. When just say I was trying to find the total reactance, I'm not even going to say capacitive or inductive. Okay, I'm just going to say reactance. And you have to determine the difference in those reactances. Basically, what that means is the inductive reactance, the reason we do that is because it's positive, because the inductance causes the voltage to lead the current. Okay. Right. And where I'm looking at capacitive reactance, it's negative because the voltage takes and lags the current. You see what I'm saying?
So you're answering my question from 3 slides
ago. That's
nice.
why I was putting that together.
Okay, cool.
Now, since the resistance does not, in effect, cause the current to lead or lag the voltage, that means it's what? 90 degrees ahead of the inductance and 90 degrees behind the capacitance. And therefore, that means in order to find the impedance, the resistance or reactance must be added what? Vectorially.
I was going to say 45-degree angle, but I was going on your illustration.
So explaining all that, if you look up there in the illustration, you see how we show it going across and showing it being added here vectorially in the illustration. That's why that's why all of that other stuff we talked about up front got us to this point. And if I don't explain that, then you don't understand what this illustration is as far as applying this in a vectorially type calculation in order to determine what that total impedance is.
Yeah, and you should be able to use, the sine, cosine, tangent, and calculate this based on the way you have that drawn, which is really awesome. I mean, to have that in there for the trigonometry geeks out there.
And if you look at that, and we're looking at the inductive reactance, and you're going to see you're going to square that. Okay.
Right.
And you look at the values and everything that's there. By the time you square that and the resistance that we give you everything, you're going to end up with a resistance here, or shall I say your impedance resistance of 6.403 ohms. Okay.
Right.
And that's why we like to lay this out and show you how to do all these vectorially and everything so you can do these calculations correctly. Now,
Hey, I got a
let's go to the
question.
next.
I got a question real
Mhm.
quick. I know this is kind of stupid, but where would it matter if a resistor had a wattage rating? And this is probably going to be a question for next week for DC. But where would
It
you
is. I
need?
already know what you're going to ask.
Okay.
All right, we'll cover that next week. I already know
Okay.
what you're going to ask us that was,
Okay.
and we
Okay.
will break that down fully through the DC circuit. And matter of
Okay.
fact, when I do the DC circuit, I'm actually going to show where we're doing that, where you could have series circuit parallel and combination series parallel circuits.
Okay. Cool.
So
And
we'll show you.
a little cheat for your first year for your apprentices that we're gonna give you answers to your questions. For all the apprentices out there that want answers to their questions, we'll answer them too. So
Sure. Now, when I look at the resonant portion of the circuit here, basically, as we explained earlier, the capacitive inductance, they have opposite effects in the AC circuit. And basically what that means, it makes it possible for one to be used to cancel out the effect of what? The other one. Okay.
right.
So when I'm looking at this, inductive reactance increases in direct proportion to the frequency, and capacitive reactance is inversely proportional to the frequency. Now, due to this, the frequency can be adjusted to balance any capacitance in any inductance. And in other words, what that means is this: the capacitive reactance must be equal to the inductive reactance with the proper frequency applied.
Okay.
Okay. So if I'm looking
Dude,
at
like
the
who is
illustration,
doing that? Who isn't doing that anyway? I mean, come on. You know, like that's just like
I know.
normal
Well,
practice. Like
sure.
I'm just
And
kidding.
what we
I'm just
like to
joking.
show here, you got a condenser, and you'll see
Yeah.
7 microfarads. You divide that by a million, and I brought this up earlier. I thought it was 5 zeros, which I was correct. 0.507. Okay.
Mm-hmm.
You're going to take and apply that into the calculation here, and you'll see my inductance is at 12 henries. So I'm
Okay.
going to square root that 12 times that 0.0007, and then I'll multiply the 2 constant time your square root 0.3146 there, and that's going to give you for your cancel effect here per the cycles per second of 17.3471. And this tells you how to go in and find that frequency when you're dealing with a series circuit.
Okay.
Okay.
Well, I just want to let you know that there was a guy that I worked with named Henry, and he's like, dude, you guys you never give me a shout out on your show. I was like, dude, I promise you shout outs, Henry. I was like, dude, we're gonna give you like at least 4 or 5 shout outs this, so you're welcome, Henry, dude. Awesome work with you, brother.
Now, the thing I like to point out here, I've seen a lot of publication stuff. I can't even really remember, maybe 1 or 2 that even, and they're more technical books that even go in and show you how to break all this down and where you get into explaining what a resonant circuit is. Okay.
Can I
So
buy it from DeWalt? Is there a way I could just go to DeWalt and buy it from their book?
Hell if I know.
Oh, all right. Well, because that's the only way I'd have it. I'm just kidding. I'm just joking.
As I was saying, you look here, you've got your circuit set up here, and we're finding the resonance of a parallel circuit here. You've got your inductive capacitance here, and you got your inductive reactance. And you'll see, based on that type of circuit, where I have a tank circuit there, you'll see they're both rated at what? 90. And why is that? Because they cancel each other out, don't they? So that
So you're
proves the
saying
point
that
of what we were doing.
So you're saying that's 90C?
Yeah, it's 90. Now both of them are 90
Okay.
right
Okay.
there. And that's what we
Okay.
were trying to point, because it's showing the portion of the resonant circuit, and that's what I was talking about them canceling out.
Okay. Okay, got you. All
All right.
right. Yeah.
Even though
Yeah,
they're
that
both
makes
set
sense.
at that. As that's how they're both set based on what? That frequency.
Gotcha.
Okay.
Okay. Cool. That makes sense.
Now,
All right.
if I look at a resistance circuit here, we're doing sort of the same thing. And when I look at just basic resistance, it has an effect on the circuit. We're connected with capacitance and inductance, like we talked about. And when I'm talking about a purely capacitive or inductive circuit, the current either lags the voltage by what? 90 degrees C, which is what we just talked about. So that's how we're sort of tying all this in. Now, if the resistance is connected in series with these circuits, the resistance always decreases what? The flow of current, doesn't it? It's just like basic Ohm's law. The more resistance divided into the voltage, it does what to the current? Decreases it, doesn't it?
Yep.
Okay.
Acts like a resistor.
Right. So therefore, when the voltage is maximum in its positive direction, a current continues to flow in a positive direction to charge what? The capacitor. That's how all that ties in. All right.
Okay, cool.
So in a purely capacitive circuit, and you take care of the current, it drops to zero as soon as the voltage reaches what? Maximum. And why is that? Because the capacitor would be what? Fully charged.
Yep.
Makes sense, doesn't it?
Absolutely,
Okay?
yeah.
So with the resistance in the circuit, the current continues to flow until the charge in the capacitor is equal to what? The voltage.
Yeah.
Right? That explains how you get all the way over to here to understand what the resistance is when I'm dealing with an AC circuit.
So you're saying you're saying that basically you're not actually doing anything mechanical, but you're engineering that capacitor to release at a certain point.
Sure.
Is that right?
And if you look here's a good example where I'm taking the I'm doing vectorially, and you take the capacitive reactance and all of that. If I take XC, my capacitive reactance, it's at what? 4 ohms. Now remember the one I did before, I did based on what? To get the impedance.
Okay.
I did the inductive, didn't I? Here,
Yep.
I'm doing the capacitive for the resistance. Then you take the resistance there, and we're showing you the resistance is at 6 ohms, and the inductive capacitance at 4 ohms. I'm going to square both of those. And then when I square those, that'll give you 36 plus 16. Then I'm going to square root that 52, and that's going to give you an impedance for this circuit of 7.2 ohms.
Gotcha. Okay.
Now, if you notice, what did I do different there? Remember, I said XC and XL, which is the inductive capacitance and inductive reactance. When you look at those two right there, I said they cancel out each other. And if you notice, the one I did for the impedance, I used XL and squared it. Here I'm doing the resistance, and I'm using XC because both of those values cancel out each other, don't they?
Yeah, and the one thing you can do too is you can, like, if you look at your diagram on the top, that you have 2 points that are inversely proportional to each other. So on one of them you could use 1.25, on the other one you could use 0.80.
Sure.
So when they're inversely proportional to each other, you could pick a value, and that value is going to be inversely proportional to each other.
Sure. And something like this is a very in-depth little course we're doing here, because I'm doing a lot of explaining here how these values interact with everything to understand when you apply certain values in order to do these calculations and why they go there. And that's why I wanted to spend some time explaining the sine wave and then getting to that point showing how they cancel out for different calculations.
Right.
Okay. Now, the next one just sort of gets in talking about power, and basically we'll tell you here. Now, people have to listen to what I'm going to say here. If you're looking at this from the point where you have in a direct current circuit, basically what we'll tell you here, the power is equal to the product of the current and the voltage. However, when you're dealing with this is true in an alternating current circuit only when the current and voltage are what? In phase with each other. Okay. That's the difference right there. Now, when I look at power is measured in what? Watts, which is what you were asking a while ago.
Well, volt amps, I think I said watts and volt amps.
Yeah, it depends on what you're putting it in. Right. Now, the reason I'm bringing that up right now, because you had made reference of power. I wasn't really going to go into all of it, but I wanted to explain, since we are going to address power here, that the question you were asking, this is where it's in phase with each other. Okay. That's when an alternating current circuit is true, where it looks like it's a direct current circuit.
It's kind of like that whole freaking padoop. What was that? Oh, that was Bill. We just threw under the bus. He always asks us stupid questions, but no, it's fun. I enjoy it.
So when I look at this, and you have a circuit here where the voltage and current are in phase, and I look at the power here, this power is going to be equal to the product of the current and the voltage. Okay. So if the current and voltage are out of phase, then you look at this, that the product of this, the voltage and current are designated as volt amps at that point and not watts. That's what I wanted to explain to you when you're looking at the difference between watts and volt amps.
Right.
Okay.
Oh, so, okay. I got you.
Isn't that interesting? I'll say that again. Yeah. If you look at this and the current and the voltage are out of phase, therefore at that point, the product of the voltage and amperage are designated as volt amps. But if it's not out of phase, then it's designated as what? Watts. You see what I'm saying?
Yeah.
So in order to find the power in watts, therefore we have to multiply the volt amps by what? The cosine of the angle. And that's how you get watts.
Like, dude, who's not amplifying? No, who's not doing that? I mean, dude, if you guys are out there not multiplying by the cosine of the angle, dude, you guys are hacks, dude. I mean, come on. Dude, everyone does that, dude. I mean,
nobody will ever do this, but it's a great explanation for people to understand. And I'll tell you, most of your electricians out there, apprentices going through, they don't get explanations in this detail on how an AC and DC circuit work. And next week's going to be just as good as this. Now,
dude, and I got a new one for the apprentices too. I'll be like, I'm gonna look up at something and I see something fucked up, and I'm gonna say, "Hey, did you multiply the cosine of the angle when you did that?"
That's right. Now, as you look at that illustration, we're going to tell you here the voltage and currents that are in phase and out of phase with each other. And I also will note here that we're also going to talk about this. The cosine of an angle is the ratio of the side of the right triangle adjacent to the angle of the hypotenuse of the triangle. Okay. So in other words, the cosine of the phase angle can be used to determine the power of an AC circuit when the voltage and current are out of phase, and therefore such angle is the power factor of the circuit. So when the voltage and current are in phase, then the value of the power circuit is 100%, and therefore power factor of an alternating circuit is of an AC circuit is good if the values are what? In unity, and if they're in unity, that value is what? 1.
Oh,
see what I'm saying?
Okay. Yeah.
And that's how the circuit's put together. And here's showing where we have the hypotenuse of the calculation here, and we're showing you the cosine of the angles at 45 degrees. All right.
Yeah. So, and if you go into that calculation, there's another thing that you'll see obvious that's number 1 in there.
Mm-hmm.
The Colorado Avalanche winning the Stanley Cup. Yeah. Oh, all right.
Never going to hear the end of that, are we?
All right.
All right. Now let's look at this. when you're doing this calculation here, you're going to see the ohms that are there, and you're going to have the impedance. This is going to do for the cosine angle. Now, remember, how did we do ohms? We did it with a capacitance, and when I did the impedance, I did it on what? Inductive, didn't I?
Right.
Now, what you're going to do is get the cosine of that phase angle based on that. So I'm going to divide the impedance into the ohms. And so I'll take,
Okay.
and we're showing in the illustration there, the ohms are 4 and the impedance is 6. So I'm going to divide 6 into 4, and that's going to give me 67%, 0.67. So for me to determine what the true power of the circuit is here, then I'm going to take 12 here, and that's going to be my voltage. And then I will take and multiply it. Looking at the amps up there, you'll see XL up there is at 3. So I'll take 3 times 0.67, and it's going to tell you when I'm applying the formula, the true power for this circuit is basically 24.12, but it's 24 watts. I ran down, and that's based on this phase angle of what? 45 degrees. Now, I don't know how, based on what I've done so far, I've taken the resistance, the impedance, the capacitive reactance, and the inductive reactance, and I've laid this all the way out to show you how all that applies in order to take those values, because they oppose each other, to get you what the true power is. Isn't that amazing?
Yeah, and one thing I want to do a shout out to, like, all the apprentices that are tuning in. I always talk to apprentices, and you always do stuff in this triangle, like, and that's the way I always approach electrical. Is like, if A is true and B is true, then C has to be this. If C is true and A is true, then B has to be this. So you're always going to have this triangle, and it's going to help you, like, when you go to take a test, when you go to take an exam or whatever. Just use that triangle formula to help you out, like, say, hey, well, for one, the journeyman's exam is not going to be false. I mean, there's going to be some little trick questions in there. I mean, I'll be honest. I was like, I look back when I took the test in 2001, I was mad at myself because there was ones I was doing calculations on, and they weren't even asking for a calculation. They were just asking what section it was in. And I'm sitting there like, I mean, I was mad at myself. I was like, what? I mean, I passed, of course, like 97%. No, I'm just kidding. I didn't get 95% on my J-Dub. I only got 95% on the death match. But, the thing is that I look at it. I mean, even if I don't even know what my score was. I could have had a 72%. And you know what? That's good. As long as it's passing and I got my license, cool. But then you move on from that passing your test to, like, the higher learning side of it. And you say, you know what? Yeah, I passed my test, but I want to know why. Why did they say this? Why did they say that? And I've always done that, like, my whole life. Like, anybody that's tuning in that knows me knows that I'll sit there and ask the inspector, like, he'll be like, hey, you got to do this. I'll be like, why? And then he'll be like, oh, it's code. I'm like, really? I was like, damn, never heard of that code. Like, hey, can you go look it up for me? He's like, no, because it's not there. Okay, well, you already know it's not there and you're trying to enforce it. And then they get mad at me. And it is what it is. I get along great with inspectors. The last inspector I had, he would bring his code book every single time, and we'd both learn.
Sure.
I'd say, you know what? You're right on that. I can't even believe that you don't even need a strap at 3 foot on a piece of EMT. Okay, well, I didn't never looked it up before. I just always thought you had to securely fasten it within 3 foot of the enclosures. Okay, cool. Well, you popped up a code from 2008 that I didn't even know existed. Right on. But I mean, that's the whole thing, that why we love doing this is because, dude, there's guys calling me all the time on code, and I'm like, nope, that inspector's wrong, da-da-da-da-da. Then he sends me a text, and he's like, yeah, it's got to have a disconnect. I'm like, oh, okay, damn it, I'm wrong. But the whole thing is, it's like, I'm not trying to put on this pedestal and say, oh, I'm right on everything. I'm just saying, I'll look it up if you ask me or whatever. I thought he was talking about the emergency disconnect in 23085, that all dwelling units need to have emergency disconnect. I didn't know he was talking about unfused conductors coming off the meter going through the house.
Okay.
I think they'll allow you to do it up to 3 foot.
Okay.
But I didn't know that. And that's what's weird too, because like in Colorado since the 90s, we can't have a panel inside.
Yeah, I knew that.
I mean, like, it would be cool. Like, there was this one, and it was funny. One of the guys, he'll probably call me out on this, but here in Colorado, they're putting panels in the garages, and they were still giving them meters, and they're like, oh, no, what are they doing? Put panels in the garage? That's hazardous location and all this stuff.
That ain't hazardous.
No, I know, but it was like, it's weird when you get all these little opinions going around, and then everyone's, oh yeah, no, that's class 2, well, that's class 1 division 2. No. It's like, okay, well, but like the utility here is basically like, as long as we do it this way, we're good. And the way I look at it with 23079 or 23085 is basically like, it's kind of Colorado aligning with the utility and saying, okay, cool. Yeah, you know what? We'll go ahead and make the NEC the same as the utility laws. And then that way everyone gets along. And, we're not trying to kill utility workers, unless you're open all your mains first, guy that was doing the double backbed thing,
Right. I got it.
Yeah, but I mean, it is what it is. I mean, we're here to try to help the apprentices learn. And if you guys post whatever questions you want, it's awesome. We got a few comments came in,
Yeah. All right, let's heck, we're already at almost 1:45. Let's go ahead and go to the new change.
Oh yeah, good point, Jake. Garage is subject to physical damage. That's a good point. I didn't think about. Right. And it could be subject to severe physical damage,
depending on where it's located.
Yeah.
All right, let's kick it up. All right, let's take a look at the new changes for this week that we'll be looking at. You're going to see we have finally got to Article 250. We have done a lot of things.
So we're grounding and bonding this
week? There will be more next week too. So
all right.
Basically what they did here is to do some clarifications when you're looking over at 250.32, and this is where you're dealing with buildings or structures supplied by feeders or branch circuits. And they've added that the grounding electrode system, and they also made sure to add a grounding electrode conductor into this. So the reason that this is because when you look at it, it's going to tell you a building or structure supplied by feeders, branch circuits shall have a grounding electrode system and grounding electrode conductor installed in accordance with Part 3 of Article 250. And then the exception is going to talk about a grounding electrode system. Grounding electrode conductor shall not be required if only a single branch circuit, including a multi-wire branch circuit, supplies a building or structure. So all they did is to make sure and explain when you go to a building or structure that when you go over there that you are establishing a new grounding electrode system and also a grounding electrode conductor to do that. Now, when you go over to that other building or structure, when you look at 250.32B, which is going to tie in with this, it basically will tell you that neutral has to take and be isolated over there.
Right.
Okay. And, you know,
And see, me personally, I would just take a number 4 right out of the concrete case electrode and just hit the panel. You're done.
yeah,
That's what I do. You can make it complicated. But.
don't worry, because we have that'll be coming up on 250.66. It gives a little more explanation on that when I made that uh, uh, substantiation trying to explain that.
Okay.
So to me, this is a good change. Now, if you have an existing building or structure, when it first came in the code, 250.32, it was B1 and B2. Now it's 250.32B an exception. You used to could go over as full code text, and you could go over and treat like we used to do ranges, and you'd go over there and they would take, and you just take that, as long as you didn't have parallel paths or something between the two structures, I could go over there and use that neutral, and I could actually ground that in over at the panel board. So now it recognizes it for existing installations, but new installations, you don't do that. Okay.
Okay. All right.
So I'm just explaining why this is here and this clarity is here, because it's for usability and consistency with the general requirement when I get over and look at 250.32B.
Is this code making panel 4?
I'm not sure. I think it is.
Okay.
I think it's 5, isn't it?
Okay. I didn't know what grounding and bonding was. I was just curious.
Now, they did some clarification here, and this is on impedance grounded systems. And they're saying when you look over at 250.36, this is for systems from 480 volts to 1,000 volts. Okay. So there's clarification that was done here. And they also took here and explained when you have the grounding impedance device, they say it's required here to be installed between the grounding electrode conductor, and to make sure that this is clarified, and the impedance grounding conductor connected to the system neutral point. And then they even do it down below. They say if the neutral point is not available, the grounding impedance device here shall be installed once again between the grounding electrode conductor and the impedance grounding conductor connected to the neutral point that's derived from the grounding transformer.
Oh, okay.
So all they're really doing here is clarifying about it being installed where the installation is, and making sure that it's between that grounding electrode conductor and that impedance grounding electrode conductor that's connected to the system neutral point, or to the neutral point derived from a grounding transformer.
Okay. Well, Jake had a pretty cool comment that came in. Was there a change about the number of grounds counted for the volume allowance of enclosures? 4 grounds count as 1 versus unlimited grounds as 1. And I know the change you're talking about. I think that came in. Is that for 2023 or was that for 2020?
Are you talking about volume allowance for inside a junction box?
Yeah,
is that what he's talking about?
I think we covered that already. Yeah, it's
I've already covered that. What
he's like?
He's talking about volume allowance. So I'm sure he's talking about the number of equipment grounds. When you get into that, you're looking over at 314.16B5. And basically it says for 4 or less, you don't have to worry about counting. Once you get over that, based on the number of extra equipment grounds in there, you have to take that at a quarter, which will be 0.25, and that will cover that. Now, the other thing I will point out, you also can have an isolated equipment ground that will also count in there. That's not part of that calculation for the equipment grounding conductors.
Okay, cool.
Okay? And you can pick all that information. Yeah, you can pick all that information up over in 314.16B5, and that happened last cycle in the 2020 NEC. Matter of fact, we updated our illustrations and everything for that, because we had to redo our calculation and step-by-step procedure to add in that 0.25% for when you were over 4 equipment grounding conductors.
Yeah, you're welcome, Jake, dude. Anytime, brother.
Heck yeah, that's what we're here for, is to answer questions if we can.
Yeah.
Now, the other thing, they added a new G here. And this is enclosed. You'll like this, Bill. Enclosures with ventilation openings. And it tells you grounding electroconductors shall not be installed through a ventilation opening of an enclosure. I know this has been a big debate on the groups and stuff. And I
Yeah.
always said you cannot take it through a ventilation opening.
Yeah.
And they'd say, oh,
It's,
no, that's not right.
dude, this was featured in Willie Jackerson's hacks. Like, dude, his video, it made me mad because I was like, dude, you can't do that. And then he's like, where's the code? And he kept saying that all the time, like, where's the code? Show me the code. And I couldn't show it because it like didn't exist. But
Sure.
they were trying to do like the Kenny clamps and everything like that. And I was trying to fight back on Kenny clamps.
Well, this here gives full explanation on that, so I don't think anybody can argue it now.
Yeah.
So that to me is a really good change,
dude. Just like the myth of the week, that was a good change too.
Yeah. Now I want you to look at something. I just brought this up. Now, there was some argument a while back, and they were arguing about one of my questions, and it was to a concrete encased electrode. And I just said, it has to be a 4, period. I'm not going to argue with you. So what they did here, there's some clarification here in section 250.66. And I want everybody to listen to what I'm going to say here. The size of the grounding electroconductor and bonding jumpers for connection of grounding electrodes shall not be smaller than given in where? The table 250.66. Now, you argued this with them too. And if you remember, Crystal even brought this up on our show. She was talking about that you have a bonding jumper going over there where you might have a bar or something. And that's going to be based on the largest one connected to it. Okay. Yep. And then it says, except as permitted in where? 250.66 A through C. Now, this argument went on, and I posted this on there and showed this, and then they didn't even respond after that.
Oh yeah.
And what it says here, when you're looking at 250.66 A through C, you're using the size that's in those sections. When I'm sizing to a cold water pipe or building steel, then I'm going to be looking at table 250.66. Sections 250.66 A through C deals with what? A deals with the ground rod, B deals with a concrete encased electrode, and C deals with your ground ring, and that's for the size of what? Your grounding electrode conductors.
Yeah, and I think this is a good change because it clarifies that all you're doing, if you have a 100 amp service, which I've never installed before, but you have a 100 amp service, you could take a number 8, you could call it grounding electrode conductor. Then you have 2 grounding electrode conductors. You have the grounding electrode conductor from your service to connect to the grounding electrode conductor to your building, to your concrete encased electrode. I mean, that's fine. You have 2 of the same exact things, but the minimum size for the concrete encased electrode is still a number 4 that doesn't change based on a 100 amp service.
That's right. It sure doesn't. And this is helping clarify that. Just putting in bonding jumpers helps clarify it.
Yeah.
Because they realize what you're going to and you're bonding the system in. But when you go look at the installation rules in 256A, it's going to have to be the largest size that's connected over the terminal bar where they're making those connections anyway.
Yeah. And I thought it was funny when Pops was like, nope. He didn't even have to think about it. He's like, nope.
Nope, that isn't right.
Yeah.
Okay. But that's why we go through these. Now, 250.68C, this is where you're going to get into your grounding electrode connections, and that's what I talked about just now. And if you notice, they tied 250.66 in a way into this because here they talk about what? The bonding jumper connection to the grounding electrode. You see that?
Right.
In the heading. Now, when you come down and you look at one, what does it talk about? It talks about the interior metal water piping here, and they tell you they just added in here as measured where? Along the water piping, in order to clarify that you have the proper amount of water pipe within the ground. Okay. Now,
Right.
when I move forward here, you're going to see none of the rest changed here. But I do want to point out something here. When I start looking at this, you got your first two, and you got your cold water pipe, and then you got the metal structural frame. But now when I go in and I look at my rebar concrete and top electrode, it's installed in accordance with what? 250.52A3, and it tells you all the installation for that concrete encased electrode. This is installation here for that. And if you go look at 250.52A3, it says if I take and I run a conductor in there and I put 20 foot in there, what size does that need to be? Number 4.
Number 4, yeah.
Right. And then if I go look at 250.66B, I'm leaving there. What size does it need to be? Because you're connecting to that number 4. Number 4, isn't it?
Yeah.
I mean, I think all of this and coming back, changing this heading and 250.66 and add the bonding jumper connection in here, this ties all this in where all the electrodes can be connected into a terminal bar, and then naturally it's going to be size based on the largest conductor that's connected to it.
Yeah, and so I don't want to put anybody on blast, but I actually watched Christine Porter do a thing on grounding and bonding, and that's where I'm taking my interpretation. So I didn't want to do anything. I actually loved having Crystal Hunter on. That was awesome. That was like one of the best shows we ever had. But if you guys want, you could go back and look at our episodes, and when we had Crystal on, that was freaking awesome.
Yeah, it was good.
That was a lot of fun. But it was Christine Porter, and she's the one that actually gave me that interpretation that if you have a smaller size than the actual electrode, then it's considered a bonding jumper.
That's right. And that's why all that's been fixed, so they can't argue that point anymore.
Yeah, and so it was one of those things that was really awesome. I've been really happy to be arguing with all the top code guys. I loved arguing with Don Gennari. I love arguing with all these people, and it's like, yeah, you have a point. That's right, whatever, But ultimately, we're doing a code show, and we're just trying to show you what the code is. We have different interpretations. There's things James interprets. I'm like, dude, you're wrong. Whatever. James is like, no, you're wrong. I'm like, all right, whatever. Cool. I mean, if you run number 8 to an AC and it's got to be number 8 ground. He's like, no, it doesn't. I'm like, oh, yeah, go read the code. And like, and we just joke around with each other, and it's cool. We could have friendly debates, and I could be wrong. He could be wrong, whatever. But, he grew up with Mark Odie yelling at him, like, flicking lit cigarette butts at his head, as a kid, whatever, But the thing is, like, we're just joking. We're a lot of the stuff we're doing like tongue in cheek. We're not serious about stuff. Like, we're not trying to like defamate anybody's character or say anybody's dumb or doesn't know what they're doing. Like, we're just trying to be part of the industry, just have fun, just joke around. Like, who cares? Like, if you make up a story about me, that's fine. I don't care. I'm not gonna go, call you up and
there will be some inspectors that if they were there, they remember this. I remember I went down. I was on the code panel we were doing for the southern section IAI. It's the first time I ever did it, and John Minnick, he was the chief in Grand Prairie, and he set it up and everything. And boy, he gave me some hard questions. One of the guys in the audience said, "Damn, John," he said, "don't you think he's answered some hard questions for his first time?" And John goes, "Hey, he can learn." He said, "If he doesn't know, he's got somebody there he can ask." And so
yeah.
I actually did on 2 questions. I was like, "Damn, man, I don't know the answer to that." And that's how I got, really learning a lot of stuff, because I had to research and do stuff. And, and plus Dad and I go to a lot of high-end facilities where they do a lot of, especially in hazardous locations. And you get asked some questions, you better know your stuff, because, they don't ask just easy questions. And I remember I went to Los Alamos, and they had set up a thing for me, and during the whole class, I kept getting asked all these questions, and basically they were going to give a prize to anybody that could prove me wrong on anything. It was called Stump Stalk Up. And then after the class was over, nobody got a prize, and they gave it to me. And they said, "You're a
Nice.
good sport. We just want to tell you what we were doing." And they told me, and I said, man, I was thinking, man, they sure are asking some really precise questions. But they actually did that to me at one of the courses.
Dude, I actually should get that award, dude. I stumped you on NEC Live. I stumped you. What was the question? You remember it? It's on there. I can pull it up too.
I don't even remember now.
Do Transformers?
Transformer.
Class 1
Transformer.
Transformers have to
Yeah.
be listed. That stumped you.
Yeah.
That stumped you a little bit. But the thing was that
It did a little bit.
To me personally, I agree with you that it has to be a listed product. And in order for it to be a listed product, they have to do some kind of way to stand behind it. But how do you list a bunch of iron things with copper wrapped around them that, you know what I mean? Like literally, how do you list that? How do you sit there and have a bunch of bean counters go in there and like measure like, oh, fail, you use 2 inches longer copper than, you know what I mean? Like that's your bad freaking transformer wrapper.
Said that is because it comes as a unit. Well, the reason I say it's because it comes as a unit, you know, and with the transformer. That's why I said it had to be listed for that.
Well, and
it fall under 110.3 listing and labeling of equipment.
Yeah, class 2 transformers, it does. You know what I mean? Like class 2 transformers is required to be listed, but class 1 transformers, there's really nothing saying like, dude, there's a lot of things that don't have to be listed. Like,
yeah, and that's why I said when I said it depends on the transformer that you're talking about.
Yeah,
whether you just can't make a general statement for that whole thing.
Yeah, and that was absolutely correct. But I stumped the stalker. No, I'm just kidding. I'm just joking.
Let's set up tool. We're already over 2 hours, brother.
Oh yeah, all right, let's go.
We did a lot of explaining.
Sorry, guys, I was slacking. My bad.
Tool of the week.
It's time for Tool Review of the Week. Sponsored by Electricians Only Tool Review and Nipex Tradesman.
All right, all the Milwaukee guys are going to love this one. I finally threw in a Milwaukee tool. Everyone loves Milwaukee. The only thing I don't like is the price, but this is a great tool. I've used it before on gas and oil, and this thing is an awesome crimper. We use high press lugs on everything out in gas and oil, and this is a reliable tool. Comes with all your interchangeable dies, and I never had a single problem with this tool. I would recommend it to anybody that uses it. Now, I will give you a little history lesson. If you go and you put the die in there that says number 8 and you crimp a number 6, and then the inspector shows up and says, you have a code violation, then Lemonhead knows all about this. They might call you on the radio and say, you got to go fix that connection. And I thought that was really cool about these crimpers. They actually have a die imprint that goes into whatever crimp lug you use or whatever crimp sleeve you use. And it tells you what gauge is supposed to be crimped on it. So the inspector goes over there, he looks at it, sees that you got number 8 crimped onto with a number 6 or whatever. I don't remember exactly the scenario, but we got called out. We had to go back and fix it. And so that was something I learned. And you don't want to do a wrong die imprint. So when you're crimping those conductors, you have to look at the actual crimp sleeve that you're using, the wire range that it is, and then make sure that you have the correct die that goes in there. So when it crimps, it'll leave an imprint, and then that's what the inspector checks when he goes and looks at it and says, oh, okay, cool, you're using 250 MCM, got a 250 MCM range listed on that imprint that the crimper leaves on it. And then he's going to sign you off and then just heat shrink it, land it, good to go. So definitely an awesome tool. I'm glad to bring Milwaukee into the conversation, even though I'm a DeWalt guy.
You know, I saw a meme that showed DeWalt, Milwaukee, somebody else. They're all up in everybody's face arguing about it and everything. And then there's a guy sitting at the table, and he said, the guy that just uses a tool that gets the job done.
Yeah.
He just chilled.
Yeah. And that's where I'm at too, you know.
I thought that was freaking awesome.
So the price of the tool set, it's around $1,000. I think it's around $1,000. It's pretty pricey, but you can get like a whole bunch of stuff to cater to whatever you're doing, which is nice because it's battery powered. Out in gas and oil, there's hand crimpers that you could use, but they weren't gonna really be code compliant to hit all those different conductor standards, which was nice. You could get interchangeable dies for them, and then you're like, oh man, we're going to be crimping a whole bunch of 4-aught this week. So all you need to do is get the 4-aught die, then you can just slap it in there, and then you just go crimp all your 4-aughts. It was a really cool tool, but yeah, I think it was around like $1,100, the one that we got.
Oh, cool.
But I'm not going to say that for all markets, and that was pre-Biden too, so it's probably like 1,800 now. But
sure, it ain't 10.
Yeah, I don't know. It could be. It could be $2,000. I don't know. It was $1,000 when I bought it, but it was a good tool. I really like. I do use a lot of Milwaukee tools, and there's a lot of Milwaukee tools that I don't have any other choice than to use those. But it's just because they're DeWalt doesn't make it. They might make a crimper, but there was tools we were using out there where it was really cool. It had a little wire stripper, and you take your drill and you put it on the thing, and you set the depth on it, and you can just put your drill on there, and it would just strip the wire right wherever you want it. And then you put the crimp sleeve on it, and you take your Milwaukee crimp sleeve. So I had a DeWalt stripper where the DeWalt stripper would strip it, then the Milwaukee crimper, and the Milwaukee crimper would crimp it, and then I had a Milwaukee heat gun that would heat shrink it. So I was using like all three tools, and they all got along. They didn't argue the whole time. So that's what it's like out in gas and oil. Like y'all get along because you're out here by the Wyoming border, and I could just leave your ass here.
I've seen different posts on different groups where so check out my new, and somebody be pulling a full setup of DeWalt. Somebody's pulling a full set of Milwaukee. This is my brand here, brother. I love it.
Yeah, and I like both sides. I like the Milwaukee. I like the DeWalt. I like both sides. There's certain DeWalt things that I don't like. Like the bandsaw I have is kind of a little cheesy, but I really figured out the problems they have with it, and I make sure I kind of address it. Sure. The Milwaukee, like there's 10 things the Milwaukee has that DeWalt hasn't even thought of yet. Mm-hmm. I mean, like this crimper, like I say, that was the minute I saw that in the morning, I was like, okay, it's gonna be a good day because I got this thing and I could just get whatever die and I could just make it happen. It's still funny going over the radio and they're like, "Where's Lemonhead at?" And I was like, "Oh, what Lemonhead? Yeah, he crimped a die on here. It's wrong." I was like, damn it. And then I knew right away that he didn't have the right die. So he had like a number 8 and he crimped like a number 6 or something. And I was like, man. And Lemonhead, like, sorry, not trying to blast on you, brother, but that was hilarious. We're like, and he's like, we got to go fix something. I'm like, what happened? He's like, I used the wrong die. I'm like, what? It has the number stamped on it. How'd you think you were going to get by with that? Like he's just gonna not see his number 6 on number 8, or like whatever it was. But it was funny. We had to go back and fix it. It was all good. Yeah.
Well,
no, awesome show. Thanks for thanks for waiting for me, everyone. And
Oh, no
you know,
worries.
appreciate all the listeners, everyone that's watching. A lot of the apprentices. We try to keep it real and just bust it out every week for you. And appreciate everyone that participated in the Myth of the Week. That was a lot of fun. We've had like 50,000 every week. We've just been killing it. So
I think that AC course tonight, I think was fantastic. I think,
dude, you
that really
did a great job.
Thing I like about it, you go through it all to get down to the end to show you how you get true power. And explaining how it actually works.
Well, you're always pushing that envelope on that next level, and that's what I like. Like everything, all your illustrations, everything is just always evolving and getting better, and it means a lot to me that you chose a real top dog to help you out, and we'll make a group and try to keep it going, keep it evolving even more, because that's what everyone likes. So,
and that's why I tell everybody, when you look at that, it's actually put in there. It's put in a sequence for you to understand how it all actually works, and that's why we do it that way. But anyway, let's wrap it up. We're at 2 hours and 12 minutes. Dude,
this is our longest show ever. Welcome all you record holders that hung out with us for a record amount of time. And, a lot of people say long shows suck, but, it's High Voltage Live, baby.
It depends on what you're covering.
Yeah.
All right, let's wrap it up. Everybody have a good week. We'll see you.
Awesome, brother. Thanks, bro. Thanks for joining, Jake Riddle. Appreciate you joining up, sir. Thanks for all the Facebookers. Whole online academy. One of a kind. Thanks, ladies and gentlemen. Appreciate you guys. Thanks to D-Man, James Senior, Great Boy Inc. Thanks to the 2023 Electrical Code Team. Hey, that's that. Join up. Love it. Thanks to the lady apprentices. Thanks, ladies. Always have a great time, ladies. Thanks, all you YouTube subscribers. Oh, thanks to Electrical Coach Special Rob. Thanks to Electric Only